Welcome, everybody. I'm going to hand over to Eva to introduce.
Good afternoon, everybody. It's my pleasure to introduce today's speaker, Oscar Agertz. It's not working?
Is it working? Or?
It is working.
It's very low intensity.
The mic levels are low, but I guess it sounds okay in there. Okay. All right. Well, welcome, everybody. I will hand over again.
Okay, and I scream. So good afternoon, everybody. It's my pleasure to introduce today's speaker, Oscar Agertz from the University of Lund. Oscar obtained his PhD from the University of Zurich, where he was supervised by
Romain Tessier and Ben Moore. Yeah.
And Ben Moore. After that, he moved to the US, got a Kavli fellowship, and worked at the University of Chicago, where he met Andrei Gastsov and Nick Naden. That was followed by an assistant professorship at the University of Surrey, and I guess the Swedish committee was smart enough to offer him a Wallenberg academic fellowship, so that he started his group at the University of Lund. So today, Oscar will tell us about what we can learn from early galactic disks and their connection to present-day galaxies. Thank you.
All right, thanks a lot, Eva, and thanks for the invitation. It's been a lovely day today. I had non-stop discussions with very clever people, so I try to be coherent in this seminar, okay? Indeed, I will talk about early galactic disks and connections to present-day galaxies. I will try to just outline why we think early galactic disks are interesting. I will focus then a little bit on the formation of these disks. What are the conditions for this, and what do we believe are the conditions, at least within the galactic formation community? I will talk about gas-rich turbulent disk galaxies, what happens when we go to this more extreme regime of gas-rich systems. And the story around this is gas telling stars what to do. Okay? So gas will suddenly lead then the dynamics of these disks. And then a bit about clumps and bars in these early galaxies, and then finally something on connections to the Milky Way and its sort of thick and thin disks. So first of all, it's an ongoing paradigm shift. Disk galaxies can form early, so when we only had access to the Hubble Space Telescope data, disks tended to appear around redshift 2 or so. Here is a plot from Ferreira in 23. The fraction of disks was a redshift. Here's the Hubble data. And with the James Webb Telescope, the advent of this, more galaxies could be classified as disks. Right? So almost half of them at very early epochs would be classified disks. Here are some imaging here, so thanks to the sensitivity of James Webb Telescope, things that will basically be the nucleus of a galaxy. This is a linear structure around this that may indeed be a disk component. Here's another example where we see what we thought could be sort of different little lumps here, potentially dwarf galaxies assembling, and with a greater sensitivity, we see an underlying, in fact, older stellar component, and these seems to be then star-forming regions within that galaxy. Okay, so disk assembly quite early has come as somewhat of a surprise, but not completely, as I will outline in a few minutes. What are the things that we want to keep in mind when we talk about the early disks? They are likely more turbulent and gas-rich. Here is a compilation of the velocity dispersions of gas, different gas tracers, as I will get into later here, CO, C2, H1, and other emission lines. Indicating that as we go to high redshift, the galaxies are in fact more turbulent, right? Or the lines are more broadened at least. Molecular gas fractions, so as we go to high redshift, so far the stellar or the galaxy populations we look at seem to contain higher degrees of gas, right? Or higher fractions of gas. Okay, so from the local conditions, a few tenths of percent at most, for L-star galaxies, we're now seeing basically up to sort of 100% or so. So this will now change the mode of galaxy formation and evolution. Okay? So what do we know about gas accretion and disk assembly? First of all, from theory, we know that high redshift gas accretion is dominated by cold streams. We think so at least, with hot halos developing at low redshifts. This is a plot from Avishai Deckel's work with Yuval Birnbaum. Here we have halo mass, dark matter halo mass, here's redshift. If I now plot basically, and the predictions here are basically based on when can you have when are shocks stable enough? When is the energy behind the shock, in front of the shock, or sorry, behind the shock, sorry, when is that not being radiated away? Okay? And it can maintain a hot corona around galaxies. And there will then be a separation here between this cold regime and hot regime, basically. And this track I just plotted here would be a typical Milky Way-like sort of halo evolution, right? Meaning that at early times, there should be cold streams, and there'd be a hot corona filling the circumgalactic medium at later times. And this is also borne out in simulations. There are many people here in the room who's worked on this also. Here's some from my own work, where we found that this sort of proto-disk here at redshift 3 or so is assembling at this very early stage by these cold blue streams, and you have this red-hot corona around this. And at later times, as we transition into a more massive halo, then these streams are drying out, and the hot corona is what feeds the galaxy predominantly with gas. Then, of course, like there are many ideas now. What are the conditions for disk formation? So these are not completely just, this is not now going to be a list of things that have to be true, but thoughts of what needs to sort of enter a picture or a theory of disk formation. Something we can all agree on, I think, is that we need coherent accretion of angular momentum-rich gas. We need angular momentum, basically. That's to make a disk. Right? Here's an example by the work of Laura Sales, where she basically looked at a wide variety of galaxy formation histories, and she computed then sort of the angular momentum of the gas accreting in shells, more or less. And for cases where, now this predictor doesn't show it very well, but in cases where it's all very well aligned, you get basically pure disks, essentially. Okay? And when it's very misaligned, you develop things that are more compact. Okay? So coherent accretion of angular momentum-rich gas is important. Avishai Deckel would argue that, well, in addition to this, galaxies merge, right? They collide, and especially so in the early universe. And he would then say that there is actually a dark matter halo mass threshold, which correlates then with a stellar mass threshold, where mergers no longer sort of misalign the galaxy, right? And you can actually form a disk properly. So here's a plot from his paper. Okay, here are sort of angles on the sky, right? Some reference points. And what he was showing is like for low mass halos, you are being flipped around by these repeated mergers, right? So things are pointing in all directions, and gas is landing in a more chaotic way. And at some point, when you're massive enough, you're not going to be more resilient to mergers, and there's also fewer mergers and such things, such that disk formation can occur. Okay? So that's another condition we may keep in mind. A classic one is also stellar feedback, or AGN feedback processes. So feedback processes, they regulate the galaxy masses or the star formation rates of galaxies. And they also promote disk formation by ejecting low angular momentum material from the center of galaxies. So things that have been sticking to the center for different reasons can be ejected out in galactic winds and reaccrete in the outskirts. Okay? So feedback in that sense promotes the formation of gas disks in this sense. Okay? There are other ideas, and this is a bit more under discussion in the community, that we need a hot gaseous halo to be developed for thin disks, like the Milky Way, for example, to be for this to be possible. It means that we need to viralize the CGM, so cooling time should be very long compared to freefall times. Okay? Here's an example from our colleagues in the FIRE team in Caltech and other places, where they looked at the star formation rate of a Milky Way-like galaxy, and here you see it's very bursty at these early epochs, and then it stabilizes. And it's only stabilizing when you are reaching these long cooling times and you develop a hot corona. So at early times, it's very messy. You're shaking the disk by all these feedback processes. At later times, you stabilize, and you can form a thin disk. So for in this picture, then, disk formation is a late thing to happen, right? So the amount of rotation versus turbulent motions is only large at very late times, which we can argue is correct or incorrect based on data. And later on also we have then the more sort of recent ideas that in order to have gas landing in a disk-like configuration, we need to steepen the potential well for thin disk formation. So you can imagine if you have a very shallow potential well, gas is landing in a chaotic way, but if you manage to steepen it by forming a nucleus or steepening the dark matter profile somehow, then you have a guiding center around which the gas can then can land, so to speak. And this has now been developed in the last few years, and I think many of these things are coming together to form the picture of when disks form, right? And it's not quite settled yet, I would say. Okay, so now what about this gas rotation versus turbulent motions? Okay. The framework I will use comes from my own work. It's from these Vintergatan simulations. This is Swedish for the Milky Way. It's winter street. And the example I will give you looks like this. Now I'm going to show you like how is a gas disk developing. And here in blue we then have the rotational velocity. In red here we have the cold gas, which is essentially then the cold interstellar medium, and we are showing then the turbulent motions, right, the velocity dispersions of this gas. And we identified 3 phases of star formation and sort of evolution of this galaxy. There's also other works outlining this by Bullock, Kravtsov, and Charlie Conroy, and Hans Walter, and others. So there's an early phase where we have early and rapid merging, where these velocity, the rotational velocity and the turbulence levels are more or less the same. Okay? Then suddenly you develop something of a proto-disk, where this V over sigma is order of 5 or a few. And this is now this early disk epoch. You have low depletion times of the gas. You form stars pretty rapidly. This is when in the Milky Way lingo, this will be essentially where the thick stellar disk forms. Then, and gas velocity dispersions are quite large, much larger than we see in the current day sort of spiral galaxies. And then we have an epoch where we transition, we are settling the disk, and we create then a thin galactic disk, right? This is then this epoch of thin disk formation. And the idea now is, of course, like we haven't yet been able to discern sort of why do we have these transitions? What sets this, right? Likely it's because we are getting now a steepening of this potential well in the picture of Phil Hopkins and Vadim Semenov, as I mentioned before. But where is the data on this now, right? So I mentioned before that we are observing early galactic disks. So the gas kinematics now, they're coming from the ALMA telescope. Here we have some examples of this. We have C2 emission and CO emission from a range here of recent publications. I'm plotting now V over sigma versus redshift. And all of these values I'm plotting here are fairly large, right? And up to sort of a 10 or even more, right? 20. Okay? And this can be compared to local spirals where the H1 gas velocity dispersions is something like 10, meaning that the V over sigma is 20. Okay? And this has not come as a surprise, right? So we have early settling of these very large disk galaxies. We should be careful. I can also add here other gas tracers. So this was now in CO and C2. If I add warm gas tracers like H alpha, it's a bit more all over the place, but they are clearly more turbulent in quotes, right? So these are less settled components of the gas. And now we can compare this then to the numerical simulations. So what the community is seeing. One of those is the very successful TNG50 simulation, developed by people, of course, here in Heidelberg, Annalisa, and also Dylan. And when we plot this here, we see like should be compared now to the H alpha observations, because it's more warm gas, and they're doing fairly well. But of course, these very highly settled disks don't come out yet in the simulations. Some of this could very well be to the way we do the emission line modeling. So theorists will need to step up their game a little bit, potentially. What is work by Masha Kohandel and collaborators, where they look at C2 emission, they're trying to model the cold ISM. And there they will see like, well, these very massive galaxies they have in their models, they do indeed seem to overlap with the observations. So this early disk settling has been proposed a bit as a problem for the galaxy formation community. I think it's not as bad as it's has been made to be. But of course, we still need, and simulators need then to sort of focus on more massive systems that evolve into early types today, and also focus on how to do the emission line model. And there are still connections to be made in terms of what this means for why these things settle in terms of the steepening. What are the time scales for disk destructions and mergers and reformation? So are these intermittent stages of disk formation? Are they really long-lived systems or not? We don't really know. And then, as I said before, right, uncertainties in how we model the interstellar medium is still to be discussed, which I will get to in a few minutes. Okay, and from all of this, there seems to be a mass threshold for where we see galactic gas settling or spinning up. So the data I showed you here before, right, is the last few years of data, right? Here's V over sigma, here's stellar mass. And there seems to be somewhat of a trend that around 10 to 9, 10 to 10 solar masses, things become quite rotation dominated. Right? And at lower stellar masses, it's more turbulence dominated. There's a mix of different gas species here, but still the trend seems to be somewhat like this. And we can now put simulations on this. So if I put my own work on this, for example, we find that almost all simulations we have just evolve along this relation. And this seems to be also the case in many other simulation works, right? We evolve along this relation. Meaning that stellar mass is not it's a pretty good proxy then for whatever is sort of regulating then or setting the conditions for disk formation. Right? So it's still up in the air, sort of what is this the actual quantity we should look at? Is it the potential we should look at? Is it the formation of the hot corona that just correlates with stellar mass? We don't know yet, but I think this is something we are going to develop in the next few years. Yeah. So this is where this lies, right? Disks appear prominently above a few 10 to 9 solar masses in stellar mass, even here in this very, very early universe data. Okay. Now, I use the word turbulence quite a lot. I use it a bit loosely. One can do this in a more rigorous way, of course, but basically the level of disordered motions like that sort of then show up as some sort of line broadening, right? This sigma I've showed already. And the question is then, what is then driving this in these early galaxies? Is its feedback? Is it gravitational instabilities? Is there a limit to how turbulent this can be, right? Because some of these early plots I showed you, there were really high turbulence levels, in quotes. I mean, 100 kilometers per second or more. Is this really disk turbulence? And does it depend then on the different gas phases that we study? So here's a work by Team Agertz and myself from a couple of years ago, where we took the data at the time. A lot of these are now from ionized gas species, KMOS data and so on. And a relation here is found, of course, between the gas mass dispersion and the star formation rate of the galaxy. You can also plot the mass of the galaxy and the surface density of the galaxy, these kind of things. And what many theorists have tried to do, right, is to create analytical frameworks that try to pinpoint the physical origins of this relation. Right? Is it feedback, instabilities? Is it sort of transport of gas through the disk? Right? And try to tease out, as I said before, right? What is the underlying physics? This has become a little bit difficult to do, I think, with this kind of data, right? And this is the point I'm going to make is that we need to be able to separate the gas phases properly, and the theorists then would need to sort of follow the lead, right? And also separate the simulations into different emission line tracers or different emission lines. So the data is quite heterogeneous. Most of the high redshift data is ionized gas. We also have a lot of mergers of galaxies, that will make the data difficult to interpret, and they're likely, potentially not pure disks we're talking about, but they're more complex systems. And then we have, of course, the effect of beam smearing, and there's a big debate, of course, about the validity of 2D modeling to tease out the turbulent component and rotational components of the data. So to make progress on this, I think it's good to make simple experiments. Right? So a simple test now is to ask sort of, if you are a galactic disk, how much turbulence do you get for free, right? Without anything else sort of operating. So I'm going to make something very simple. It's almost stupid to do this test. Right? So I'm going to take a high redshift galaxy condition, like a very high gas fraction galaxy. I'm going to run it without feedback, an extreme case where feedback is inefficient, so you have fragmentation like this, and one where I do my feedback, stellar winds, radiation, physics, all of this. Right? So I regulate star formation. I puff up the disk like this. And now I'm going to check sort of what is the level of turbulence in quotes, meaning like disordered level of disordered motions, and I can now plot this sort of on this relation I showed you before, right? And these contours now are like patches, kiloparsec scale patches in the galaxy, right? And this sort of data, this point here is the galactic average, and you can see like in principle I can see no difference here, right? And they're very similar, which means that a galactic disk tends to sort of give you whatever it needs to reach some new stability. Obviously, the morphologies are wildly different, right? But this is the way disks behave. So I get the same level of turbulence here, maybe 40, maybe 50 kilometers per second, nothing more. There's no way I can reach this under any conditions I try for this object. The ISM structure is very different, but average over large scales, they establish the same sense of stability. This sort of Thunberg-like stability, right? Where things are marginally stable. Okay? This is also something we can see in local observations, right? Galaxies tend to stabilize to a parameter of this Thunberg parameter of a few. Okay? And okay, so then the question is like, is there really no signature at all of the feedback effects, right? That we would think would shake the galaxy quite a bit. So if you now split this up now into different gas tracers, here we have the CO, and now I take the relevant data, right? So I take the CO data, the H1 data, and I plot sort of my simulations on here, a low gas fraction one and a high gas fraction one. And then I do the H alpha, so the warm gas tracer. And here we can see quite a dramatic effect. Right? So once I go to the sort of warmer gas, a lot of these turbulence that is observed is in fact sitting in outflows and fountains. It's not really disk turbulence as such. And it's only if I turn off my feedback here, right, I actually can see an effect. Okay? So, so the warning, it's a bit of a warning here, right, that if you're going to use ionized gas tracers to talk about disk physics, you have to be careful, right? Some of this is not really sitting inside of the ISM, but more in the outflows, and you will be biased to very large, and infer turbulent process dispersions. And you don't need much energy for this, right? Like 10% of the total turbulence energy budget, right? That's what you need from the feedback. So it's very little energy to power this diffuse component. And this offset of 2 to 3 I'm showing you here is also observed in nearby and also high-redshift galaxies. So it's something that's been confirmed now, I think, by observations, right? This offset from here to the neutral gas is something that is confirmed by observations. So what about this sort of, now the CO layer, right? So the molecular gas in these galaxies, what does this do to the stars that are forming, right, in these disks? Well, one thing that comes out of this is that is the following. So here I'm going to plot the velocity dispersions of the stars at birth, right? It's essentially within 10 million years of their formation, what are the velocity dispersions? And as a function of the gas fraction. Yeah? And again, right, these galaxies, they are identical galaxies. I've just changed the gas fraction. That's the only thing I've changed. And if I go for the high gas fraction case, stars can be born in a very thick configuration because the molecular layer is very thick. And then around 20% gas fraction, things calm down. And we are reaching more like Milky Way thin disk kinematics, right, for the stars. An interesting thing then is that this sort of level of turbulence that is driven in the galaxy by feedback and instabilities, it will act like a barrier against thin disk formation. Right? So, for example, the Milky Way cannot have had 50% gas fraction, 6 billion years ago, right? Then it would be too much thick disk forming. Right? So I think the gas fraction here is really a controlling parameter for the level of turbulence via both gravitational instabilities and stellar feedback. Another interesting thing that comes out of this is that the eccentricities of the stars, because now, as you may have noticed, this has a lot of lumps, massive GMCs inside of it. What happens then is that you get very rapidly, you're scattering your stars onto eccentric orbits. So for high gas fractions, you get an eccentricity distribution centered around 0.5. Okay? And remember, like 0 is perfectly circular orbits, and you have to decrease the gas fraction in order to reach the thin disk distribution here. This shaded region here is the thin disk distribution for the Milky Way. Right? So the Milky Way has likely been somewhat gas poor for quite a long time if we have a substantial amount of stars sitting in these sort of low eccentricity orbits. Okay? So that's one way that the early universe properties of galaxies affect both the gas and, of course, also then the stars. So now something then on the clumps I just mentioned. Right? So high-redshift disk galaxies, they tend to be more clumpy and more unstable. Lots of work is done on this. Large fraction of galaxies at very high redshift are clumpy, maybe even up to 80% above redshift 4. Right? This is now coming from James Webb observations. We've known this for quite some time. This is the Hubble Space Telescope images published by the ALMA greens in 2009. Of course, these are rest frame UV, so we only saw sort of these sort of large, unresolved, star-forming regions, basically, right, or bright spots, bright UV spots, basically. But these sort of regions then were very massive, even up to 1 billion solar masses, and it wasn't clear, like, are these really star-forming clumps? Is this internal structure of galaxies? Are they mergers? Right? And with the James Webb Telescope, you can do even better, of course, and in not only in terms of observing the underlying old disk, but thanks to lensing, we can now probe the mass function of of stellar clumps down to, even, a few tens of thousands of solar masses. There's a great diversity of clump and cluster properties are seen. Some of in the lens galaxies, they go as deep as, or they go to sizes of protoglobular clusters, like parsec resolution. Right? So we see a very highly fragmented state in most of the galaxies that are looked at, especially with lensing. Okay? They're quite dramatic. And the question then is, why are they so unstable? Huh? What is driving the general instability of galaxies? Right? And this is something that's been studied for quite a long time. Right? What is behind this? And I know it's sort of breach of good taste to show a lot of equations in a colloquium, but I will do that for a few minutes. And this is one of those things that you encounter when you do galactic dynamics or study the stability of galaxies. So basically, if you take now your Euler equations in some sort of cylindrical coordinate system or polar coordinate system, you do a perturbation theory on these. You perturb the densities and velocities, etc. And you assume they are plane wave perturbations. And then you assume a few other nasty things that makes it very restricted. Single component, these are 2D disks, axis symmetric, linear perturbation, all of these kind of things. Right? What you then get out is a condition, right, where this sort of omega square is positive, you're stable, you have oscillating solutions, right? This is basically the Jeans criterion plus shear, right? So it's something very simple. When this is negative, you have an exponentially growing instability, right? The exponentially growing, which is what instabilities do. Right? And from this criterion, this dispersion relation for the wave, we can derive this sort of famous Q instability criterion for disks, right? When Q is less than 1, you're unstable. This goes back to even the 50s, right? And in terms of stability of rotating ellipsoids and such things. So why do I bring this up? Well, now we can make this sort of, plot this dispersion relation here, where we have here, dispersion relation here, which will be the growth rate of the instability, and as a function of scale. Right? So this is the inverse of the scale. So this is now very large scales, this is small scales. And what you can do now is you can repeat this exercise that I outlined, but do it both for stars and gas and combine them. And this has also been done for quite some time, and there's some seminal work from Chanda Jog and Phil Solomon in '84. I think this is Chanda's PhD thesis, or PhD work from the 80s, where she beautifully said it this way, right? Even when only a small fraction of the density is put in a cold fluid, that is gas, like 10 to 20%, and the initially stable star-alone system becomes unstable. And this is sort of the plot she made. This is now the dispersion relation for a stellar-only disk, and you just add a little bit of gas, 10, 15, 20%, and you destabilize the disk, over a wide range of scales. Okay? Same mass, nothing has changed, but it's really just like adding in a little bit of gas. And so this is the reason why, like gas will start to drive the instabilities, quite strongly so. And there's more work to do this in a more sophisticated way in the literature, of course, today. But if you now compare this to simulations, this is, of course, very well, this was linear stability analysis. If you now do this in terms of the simulations, you see something like this. So now, here I take a Milky Way galaxy, disk 5 times 10 to 10 solar masses in a dark matter halo of 10 to 12 solar masses, and I run this here, right? It's a low gas fraction, and you see the spiral arms here, you see little clouds along the spiral arms. Right? And now I keep exactly the same, repeat this, no change, I just take some stars and switch out for gas. Okay, so the same disk mass, all of this. Right? And I start then to destabilize the galaxy, violently even. Okay, so for high gas fraction here, you develop all of these clumps right, inside of them. So gas couple more strongly and drive instabilities, clump formation, and high levels of turbulent motions because of this, right, or disordered motions. And this is the reason also why we saw these very eccentric orbits I mentioned before, right? These clumps now going to scatter stars quite violently. So above some threshold, we have a few tenths of percent in terms of the gas fraction. We get more clumping turbulent galaxies or disks, and the gas will start to lead the stars, right? That's the whole idea. Okay, and one can then ask the question sort of when is, how are these clumps developing? Or do we see here, is it gravity or feedback that's driving the turbulence giving rise to the clumps? Is it gravity and feedback or gravity then feedback? What do I mean by this? So there's some nice work here by Jeremy Fench, where I like these experiments, right? So he took an isothermal disk, a constant temperature, no fancy feedback, nothing, right? Gravity and hydrodynamics, right? And then I think that's it, right? Gravity and hydrodynamics, no star formation. And then he let them fragment like this, right? So this is a local spiral, an early universe disk, right? And then he showed, like, look, in 10 million years, you develop cloud mass functions that are in agreement with the local universe observations. Okay. I believe these are the GMC, yeah, these are the GMC ones. This is very much like the Milky Way GMC mass function. This will be then the higher redshift galaxy one extending to higher masses. And they said, so gravity is enough, right? This is setting everything. Then my own work on this, well, I have to flash this, of course, is saying, I think Jeremy is correct. But the problem is, like, if you don't do any feedback here, the clouds are long-lived and they grow to be very massive. Right? So here I'm comparing, like this black line behind here is the Milky Way data by Hare, 2009. And if I then don't do any of my disrupted clouds, I'm going to have way too massive cloud mass function. And then what happens is that the role of the feedback is then to disrupt the clouds, bring the mass back to large scale, and do another cascade. Right? So to maintain the cycle of forming clouds, you need the feedback to be the cycling mechanism. So I think that seems to now be quite well established, right? That it's the duality of gravity and feedback will both operate to form the cloud populations we see in local spirals. Yeah. Okay. So now switching gears a little bit to other types of instabilities, bars and spiral structure. Right? This is something that has been emerging also since the James Webb observations. There's an existence of high redshift mature disks where we see spiral structure and bars. 30 to 40% of these disks likely have spirals. Often they are clumpy spirals, as I said before. There's a bar fraction that was much higher than expected from a few years ago, 10 to 20%. In this redshift greater than 2 disks. Right? So pre-James Webb estimates were 0 to a few percent, right? And now we have at least a sizable fraction of them featuring bars. And here you see them, here they're color-coded, right? This is now the redshift, mass, and the ones, on the squares here is where we have bars. Here's an example from Luca Costantin's work where they looked at the Milky Way-like progenitor that seemed to have a very large linear structure, likely a bar. Okay? So, the question is, like, this goes a bit in the face of how we thought bars would emerge. We think of that as a low redshift phenomenon in more sort of colder disks, settled disks. So how can these form now in these more extreme objects? So one thing you can do now, you can do n-body models of this. Okay, so as a work done together with Josman Hawthorne, Tor Tepper-Garcia and others, where you can now study what is the growth timescale of bars. Right? So you take the galaxy, you do some azimuthal Fourier decomposition of the density field, and where you now have this sort of the A2 over A0 right, components, where this ratio of these two components from the Fourier expansion is large, then you have a linear structure in your system, right, like a bar. Okay? And what we can do now is to measure this exponential increase of this. So instabilities are growing exponentially. So this is now sets my exponential growth time scale for the bar. And when you do this, and this is not only we have done this, Michiko Fuji has done this at the University of Tokyo. You can now look at what is then the bar formation time scale versus the amount of mass you have in the disk, right? And it's actually quite a beautiful relation between these two quantities, right? So for very baryon-poor systems, it takes the age of the universe to form a bar. And for baryon-rich systems, it takes maybe 1 billion years or 2. Right? But the problem is that at earlier universe, redshift 2 or so, the universe is less than 4 billion years old. So if these have bars, you have to first form the disk at some point, and then very quickly then form the bar, right? And it's very difficult to imagine this for very low efficiently star-forming galaxies. All galaxies will have to be very baryon-rich then for this to be possible. And in addition, thick disks are thought to have even longer bar formation timescales. So thick in terms of the turbulent driving, you're driving these sort of very high velocity dispersion, thick gas disks. This is thought to be inhibiting bar formation. So the question we ask, what happens if you add now or model now the turbulent motions as well, right? If you have a multi-phase turbulent disk. What we found was pretty surprising. So we ran something which is a Milky Way-like progenitors here. So 10 to 11 solar mass dark matter halo. This is like an LMC-like setup, which is the Milky Way at redshift 3. And the bar formation timescales are predicted to be long, maybe 1 or even 2 billion years for these, right? And what we found is that now, like here we now increase the gas fraction. What we found is that the presence of turbulent gas completely speeds up the formation of the bar. Right? In the most gas-rich case, it forms almost immediately, and it actually destroys itself. It becomes too mass-loaded, so it buckles, and you form a bulge instead. So what happens is that so you speed up based on the gas fraction. We find that the bar is the progenitor of the bar is a 3-armed spiral with then the third arm folding in, and then you establish the bar. And what tends to happen if the bar actually survives for some time, you see here, right? If you only run this now for a few 100 million years, right? Less than a billion years, and this has already been destroyed, right? And these other cases, you develop then a very strong radial shear flow, and you feed the central, you see the central part of the galaxies with tons and tons of gas mass. So the bar will eventually be destroyed when you develop these inner limbless resonance. You then form a nuclear stellar disk, gas disk and stellar disk, and we believe that this is likely something that if it happens in the early universe and you're gas rich, you will not see this for a very long period of time, unless you reform the galactic disk. So if you put this now on a plot like this is from Anna de Graaf's work, where here we have the dark matter fraction. So the sort of 1 minus this is then the baryon fraction in the disk, right? Versus redshift. And here we have sort of the predictions from the TNG50 simulation, and here we have different estimates from the literature. Right? So fast bar formation, like the ones I just outlined, ought to be quite easy to occur when at around redshift of 1 to 3. Right? Many of these objects have enough baryons in them to drive fast bar formation from a bulge in the nuclear star cluster, etc. Right? So it's bar formation is sped up by turbulent motions. In the last sort of 5 minutes or so, I will now make some connections now to low redshifts. So other than memories of this turbulent past in the Milky Way's disk, or disks in fact, I already mentioned some of this before in terms of the eccentricities and the vertical velocity dispersions. So just to connect back to this, this is the picture I'm in, right? I showed you this before, right? The amount of gas rotation and turbulent velocity dispersions. Okay? And what we're after now, what I'm interested in sort of showcasing to you is like how do you go from this fixed stellar disk formation scenario where we have lots of gas turbulence to a thin disk. Right? So what's happening in this transition? Right? And what I want to do now is essentially just to give you examples from cosmological simulations. Right? And I know many people in this room are really experts on stellar populations, but just to bring us all on the same page, I still want to highlight very briefly what we think the Milky Way structure is, right? And this is a theorist view of the Milky Way, so you can see how how accurate this is. But very broadly, in very broad terms, we have a thin and extended stellar disk that is fairly kinematically cold. Most stars are younger than 8 billion years, and we are poor in alpha elements, so these multiples of helium nuclei. Right? And then we have a thick disk that is somewhat shorter and thicker, kinematically hotter, older stars, and rich in alpha elements. There are many, of course, caveats to this picture. We have flaring, we have coeval formation, and these kind of things. But the overall idea is somewhat here. And what I'm after now, okay, and the thick disk, we have known this for quite some time. The geometrical thick disk have been known, even before, but from Gilmore and Reed in '83, where here we can plot the sort of distribution of stars as a function of height above the disk plane, which is well fit by 2 exponentials. What I'm after now, and see, I want to understand if there are traces now in the chemical thick disk, chemical thick and thin disk. Okay? So I want to see, what can we learn something about how gas was accreting onto the galaxy this way, and how we transitioned from this early turbulent state to a more well-behaved thin disk. Okay? So this is also something many of you are aware of, but again, I'll repeat this for clarity. So if I now plot the alpha over Fe, the abundance of alpha elements with respect to iron, and here we have the metallicity of the stars. If I do a simple galaxy formation or chemical evolution model of this, I expect at early times we have a high alpha enrichment due to core collapse supernovae, where we have lots of alpha elements enriching the ISM, and you form stars out of these. Type 1a supernovae become important at some point. And you have a greater contribution from iron relative to alpha elements, right? Or at least it's more of that. So you're going to have a knee forming like this. This is also borne out in observations. Many examples of this. This is work by Thomas Bensby and Lund. We also quoted them by some estimates of the stellar ages. So all good so far. But the Milky Way actually has a bimodal distribution. So there's actually a trend down here where we have, for the same metallicity, we have a bimodal distribution then of alpha elements, and these are all younger stars. And the question is, like, is this cosmological infall of low metallicity gas? Or can it be other effects, like radial mixing of stars from different birth sites, I should say, right? That create this sort of locally in the solar neighborhood, we observe this bimodality. So this, I think, is something, in fact, that tells you a lot about how the disk itself formed. So I will give you an example of this in the last few minutes, right? This is an example from our simulation here. There are many other people who have done similar efforts also in the last, 5 or 6 years, right? So, and I'll probably show some of those results if I have time. So what about inflows, last major merger, and disk formation in this Wintergatan model I showed you before? So what we have here now is the main galaxy. This is now in this turbulent early state, high velocity dispersions, right? And it's pretty small, okay? This is the size of the star-forming disk versus redshift. Here's the last major merger, okay? And I'm gonna play now sort of the evolution of this, right? So now we have this falling in. It's a cosmological infall, right? So what happens is that you're driving in lots and lots and lots of gas onto the galaxy. And what you see here now is almost like a doubling of the size of the disk. So all this gas wraps around the galaxy. If we look at the metallicity of this gas, here in yellow, it will be the metal poor gas coming in, wrapping around the disk. And the blue here is the metal-rich gas. Okay? So you're building an outer disk that is metal poor, in this case. And then we can keep this going, and the galaxy will be keeping fed by the circumgalactic medium instabilities in the halo and such things. Right? Okay? And after this, it's transitioning more to gas-poor, more well-behaved, simple state. Okay? And the rapid growth here is not only seen by us, as I said before, but in many other high-resolution simulations. The physics, again, is inflow from the CGM, like a lot of it at some time. Optimal conditions for gas accretion. We have lots of baryons around, lots of perturbations, rich in angular momentum, and we don't have any more of those disk spin flip I mentioned before. So the disk is quite well aligned, right? And you can accrete in a coherent manner. And this could be contrasted with simple chemical evolution models, like two infall models, right? You have another infall of gas that makes this. But the gas is not really landing necessarily in the old ISM, but you form a new disk around it, which is more pristine in its material. So if I now turn to the stellar populations of this galaxy, we look as follows. Here we have metallicity, here we have age. Here is this alpha over Fe metallicity plane, and here's the epoch of the last major merge, right? Where we had lots of gas infall. So here's how it builds up. Okay? So we have an early enrichment. This is the inner galaxy, essentially. A lot of this is in situ and accreted, a mix of both. Okay? And we can tease out starbursts and dwarf galaxies inside of this cloud, in principle. Then we go into this sort of epoch I showed you in the movie before, and we form, in fact, a low metallicity little tail here. Right? So this is metal-poor gas accretion and the onset of the thin disk. Okay? And again, other people have seen very similar things also recently in their simulations. And then after this, the interstellar medium will start to mix together. You have radial migrations of stars, and you create now a fairly simple age metallicity trend, right? And you're then also filling in here, right? This sort of low alpha ridge, right, of the alpha over Fe metallicity plane. The clumpy disks at these early epochs, it looks a bit crazy. You have an inner disk that's misaligned. Everything is straightened out by redshift 0, more or less, right? And it's a bit of a warping here in the stellar distribution. And what's interesting about this, man, is like we have then this idea of that we have an inner galaxy forming, and when you have sufficient gas accretion occurring and it's landing in the outskirts, we can then develop this sort of low metallicity trend that also then builds the start of a thin disk, right? And this is also then, the qualitatively borne out in observations. This is by Chiukat and collaborators using Apogee Gaia Kepler data, to do some machine learning approach for the ages of the stars. And here are the guiding centers of the stellar populations of the stars. And here we have then the inner galaxy forming, and at some point we have this really outer disk appearing, right? And in our simulations, we would argue that this obviously is then the gas accretion from cosmological scales. And then you see a similar picture as I draw up here, right, in the alpha over Fe regime. We can compare it more to sort of work that's been done here locally in Heidelberg, Chiang and Rix. There's a nice paper on time resolved picture of our Milky Way's early formation history. And there are overall interesting trends here where we see this sort of in the local, in the solar neighborhood, we have this sort of angular momentum poor inner population of stars sitting here. And there seems to be some evidence at least, right, for a reboot of disk formation happening maybe 80 or so billion years ago, right, which is here. Okay, so this is like, we happen to qualitatively match this, and I think it doesn't need to be as specific as one can imagine. We just need to have an epoch where we have a lot of gas infall. The fact that it happens around the last major merger is just even affecting the simulation. Yeah. So that's the connection I want to make to the Milky Way. And so let me just move then to the conclusions, because I'm hitting the 45-minute mark now, I believe. Dynamically cold disks at high redshift and the so-called James Webb ALMA revolution, massive disks can settle already within 1 to 2 billion years after the Big Bang. Is this a problem for theory? Many people have asked this. So there are many factors that affect disk formation and settling, angular momentum, aligned gas accretion, lack of merger-induced spin flips, all these kind of things. Right? And simulations will, they will predict different timings of this, right? Because of the implementation of star formation and feedback physics. Okay? But I think so far this seems to me at least not to be a crisis yet to understand these very early and also very massive galaxies. Right? So some models get them right, some don't yet, and I think it comes down to the details of the physics we put into the simulations. For high gas fractions, gas drive or dictate disk instabilities. This is a classic result in some sense. How it manifests itself in terms of classic linear stability to clumps and clusters. That is actually more complicated, but the idea, the concept is understood. How turbulent can disks become? Can they be as turbulent as the data I showed, hundreds of kilometers per second? I think not. I think if you're a disk, if you see those levels of velocity dispersions, you're seeing maybe outflows or mergers. Disks seem to not be able to drive more than roughly 50 kilometers per second or so, right? Even for very high star formation rates. Bar formation times got sped up when cold and turbulent gas is present. The physics behind this is not quite understood yet. It likely has to do with the turbulence being able to kick stars and trap them onto bar orbits. There's some work we are preparing on this now, but it's complete. It's at least it's manifesting itself in the simulations. Gas turbulence and clumpiness shape the eccentricities and dispersions of stars at birth. So there are, in fact, observational imprints if turbulence is strong enough in the molecular star-forming gas. And then the connections are made to the Milky Way. Thick and thin stellar disks. This chemical bimodality that we saw, I think, is indicative of disk growth and the transition from the regime of thick disk formation to thin disk formation. Okay. With that, I'll end there, and thank you for paying attention. Yeah.
Thank you for this talk. I'm happy to open the floor to questions, particularly from students and postdocs.
Hi, thanks for the very cool talk. If you can go back to the slide where you showed the disk with and without feedback.
Let's see. So you mean this one?
Yes, exactly. So you said you compare like the sigma measured on a galaxy level, but what happens if you measure the sigma at like individual patches, like at small, let's say small voxels, right? Then the regions where you have this clumpiness, do you expect the sigmas to be higher and then the median sigmas would be higher compared to the case where you have feedback?
I think it's a very good point. I mean, just to reiterate, we indeed compute things here at the kiloparsec scale patches, right? So this is why I use turbulence in quotes, right? Because clearly here, we are looking at disorganized motion, basically, like cloud scattering, something like this. Here, maybe still so, right? But it's still more, if I plot, which I have done, and I have the plot somewhere here. I can plot the 3D kinetic energy spectrum, and we have an inertial range. We have things that should be part of a discussion where turbulence fits, right? Here it's much less so. We don't have anything like an injection scale and an inertial range, right? So they are just very different in terms of this. But then the question then is, of course, like, if I now look at this point here, is it more turbulent than it would be than a cloud here, right? And I would say we haven't checked this. What Well, actually, no. We actually we have looked at real parameters and loss dispersions of these ones. So these are extremely massive. So all of these kind of clumps will be much more turbulent than any clump here, right? But in terms of the average, what you're picking up is the sort of cloud motions, and those are essentially then similar to what you get here on the same kiloparsec scale. That's all I can think about the question a bit more carefully and get back to you, of course. But yeah, we don't measure that effect that you maybe after.
Hey, thanks for the cool talk. In the next slide, or maybe a little earlier, you had the difference between H alpha velocity dispersions with and without feedback. Do you also have this for the CO or the cold gas? Does it respond at all to
Yeah,
this?
no, yeah. So yeah, the for the CO and H1, they're just overlapping completely.
Ah, it's sitting on top. Okay.
Yeah. I mean, I don't show them in. Yeah, I have the plot. Yeah, they're basically just within a few percent or whatever, 10% from in terms of values. Yeah. So it's and again because they're measured on fairly large scale, kiloparsec scale.
Yeah. And second question I had was the dispersion relation analysis you showed by the joke paper. But you have the same. You change the gas fractions by just swapping the stars for gas. But what happens if you change the dark matter fractions, for example?
Good. Yeah. Okay. So this is if you change the dark matter fraction, what you would change then is, I mean, so these are then the parameters, right? So if you're in a disk, what it comes down to then would be this. If you have a dark matter star gas system, right, it would be then the surface density of the dark matter that would mean something, right? And that is very low, right, compared to the stellar and gas one, right? That's So it's not me. Yeah. So it won't be. You don't need to include that component because of the low sigma dark matter, basically.
Yeah. Okay. I was just asking if you did have a very high dark matter surface density.
If it's extremely high, then of course, I mean, then you would in the end your rotation curve will be rising and not flat. You would change some of the shear, of course, depending on a bit of this, right? And if it's completely dominating, right? Then it's the surface density of the dark matter in some sense that will dominate the gravity locally, right? Yeah.
More questions?
Hi, thank you for your nice and detailed talk. My question is that in your talk, you mentioned that the steepening of the gravitational potential is essential for forming a thin disk. Also, cold gas will somehow will somehow destroy the stability of the disk. However, in local universe, we observed many dwarf galaxies that have chord profiles in their center, while they are very still thin, and also they are very gas rich. So do you have any comments or explanation for why these galaxies are stable, especially there are some kind
Would
of...
you say something like WLM or something like this, I guess, right? Would be because
Yeah, I mean, like some kind of low surface brightness galaxies, some kind of super thin galaxies, they find that it is very thin, gas rich with core profile inside.
Yeah.
So do you have
Yeah.
any
No,
comments?
I mean, I think it's an excellent question, right? It would mean like in that simple picture of a potential steepening, right? Like to assemble the disk properly at first, right? You would demand that it would be a steepening, right? And so in this case, of course, to get the core profiles, if it's really like a core profile, right, then you need to drive in a lot of baryons for that core to appear because of the oscillations of the potential well, right? So there are a few more steps there to fill in, I would say, right? You need to form a disk in the first place, create the core, and then whatever is left then later on, right, would be whatever thin disk that you manage to assemble anyway, because you have already gone through those steps of steepening. That would be on top of my head sort of how we will go, right? But because of the coring, you need to have lots of baryons in the center anyway at some point, right? And,
Okay, and how about the gas fraction? Because these super thin galaxies are usually very gas rich. I mean, the H1 gas, I don't know if it is inside your definition of cold gas here, because you do not show whether it is molecular molecular hydrogen or H1. These galaxies have very high H1, but they are somehow very stable and very thin. Is it contradict to what you have talked about?
No, I mean, if they are very extended and you know, let's say the surface gravity, so to speak, is very low, right? Then you don't have, you know, then you can settle to something quite diffuse and featureless. I'm not sure if these are the kind of objects you're talking about or not, right? I don't know if you have, you know, these very low surface brightness one in terms of the stars also, they have enormous H1 disks, right? And even a lot of 50% of early types have these disks also, right? There's, let's say, non-star forming H1 disks that are they are very stable. So they're not really, so this is, and some of these, at least in models, they tend to form at late stage. You have high angular momentum material accreting late, so you get these very extended systems, but they are gravitationally very stable also, right? So you're not going to be worrying about turbulent motions and such things from feedback or anything.
Okay, thank you very much.
But we can talk more, yeah.
More questions? You can meet me in the middle.
Oscar, you portrayed the bimodality, the chemical bimodality of the Milky Way somewhat as a natural consequence of its formation history in that context. Now, there is evidence that M31, which looks similar, may not have such a chemical dichotomy or bimodality. Is that comparably plausible, or is that surprising?
That's a very good question. I may have sort of somewhat misrepresented this, I guess, because it's not a natural outcome of disks in general, right? The way it occurs in these models I just showed here, right, is that you need, in order to create something that is poor in metallicity, that also has a different alpha, right? A few more conditions. So if all of this gas, and maybe I can even go to the one that you have also been involved with that, like all of this gas, if it landed in the inner disk, you would just dilute this, right? And you would not reboot, you would not see something that starts at a lower metallicity. You would just dilute this, and you get the knee, right? Like M31 seems to maybe have, right? Here, what happens is that you form an outer disk. It's compartmentalized from the inner disk to some degree. And if you form enough stars, you have a strong bimodality, and that's basically half of the mass of the system. And of course, there's still, if I move this down a little bit, right, this sort of low metallicity gas coming in here, it also dilutes the inner galaxy. You see up here, right? I think there's a bit of a trend here also, right? There's a dilution of the sort of the ISM that also makes this sort of turn down as well. Right? So the gas will accrete, but there has to be some component of it that's rich in angular momentum, so it can safely then lead to what I just described, I guess. That's the whole thing. But we don't have. I mean, there are statistics on this from the cosmological simulations, like the TNG50 model, right? And I think those pathways are somewhat aligned with what I said now, right? But we don't have as many models where, let's say, you have a cold ISM components, with good statistics of galaxies. We don't have those kind of models yet.
Question.
I have one more question. When you showed the turbulence versus gravity-driven regulation.
This or no?
No, after this, like you briefly talked about.
One of these or?
Oh no, like where
For the cloud formation? Or?
Yes. Yeah.
Oh, here,
I think one slide after. Yes, exact. Yes.
Okay, yeah.
Right. In this kind of setup, right? So the feedback is, I'm assuming it's still a feedback, but if you do not have stellar feedback, but still have cosmic accretion, the cosmic accretion would drive turbulence and then also destroy the large-scale clouds, right? So I'm not quite sure, like, what to take away from this message. Like, is this dichotomy, like, resolved? Or
I mean, the point of this one is to say, like if you just shatter a disk, right? Yeah, you have some shear, and you can extract clouds from this, right? If you have, what happens here is, like, this is 10 million years. So in quotes, I say one cascade, right? So you have one so large to small scale cascade, and then you get this out. And if you kept having cosmic accretion on this, these clouds will still accrete material and collide and merge all these things, right? That clouds tend to do if they are left alone, right? And so your mass function will likely still be, it will be too high. You have too many massive clouds still, but you can still maintain that cycle, right? You can form new clouds, right? Because the disk is being fed by more gas that will become unstable. Right? But remove that factor for now, right? And what you get is that you need to stop star formation at some point in the clouds, redistribute them, and then what you have, what I didn't say here is that this mass function is kept for like 1 billion years. It's invariant in time, right? Because you're cycling and you're establishing this mass function, right? So it's not like a coincidence over whatever collapse time scale, right? It really is maintained, right? But the point is that these are not incompatible. It just means that gravity plays a very big role in driving the turbulent or disordered motions that lead to cloud formation. And you don't really need the supernova feedback, whatever you want, right, to do that in principle. So the role of stellar feedback in order to drive turbulence in galaxies is not as obvious as one would think, right? You can do it with gravity and galactic dynamics alone, potentially. Yeah. But don't quote me on this.
So before we thank our speaker one last time, I'll just announce there'll be drinks with the speaker organized by Marco and Francesco. And so you can come and meet. That'll be at 6. So you can come and meet with people up here to go for that if you're interested. And there'll be dinner at 7:30 at Urban Kitchen for those who've signed up. I think there maybe is 1 spot free if you're interested. So then let Ava know if you're interested.
This will be on YouTube, I guess, later on, right?
Your talk will be,
Yeah.
yes, you will be a YouTube
I told
star.
my young sons I would have to say, like and subscribe, right?
Like and subscribe. There we go.
So, yeah.
Thank you very much for the
Yeah.
All right, thank you very
Okay, very much, yeah. Is that, yeah.